Okay. So, we are in the discussion of primal methods, right. Now, in the last lecture we discussed the basic issues of primal methods and discussed generalized reduced gradient method, and in that we use the slack variable formulation. Now, we will in this lecture this lecture actually will be in two parts. In one part we will discuss gradient projection method and the other part we will discuss the feasible direction method. So, this gradient projection method we will study with the active set formulation in mind, and as I told you earlier, for any of these two GRG and gradient projection you can do the other formulation also, gradient projection method. Here since we are going to take active set method, so we are putting in the beginning equality constraints separately and inequality constraints separately. Out of the inequality constraints, whichever are active at any iteration, they will be included in the list of H, fine. So, choose a starting point which must be feasible and set the iteration number 0 and select a tolerance, okay, a small number below which you will consider 0, and then you start the loop. In the loop, first of all at the current point you decide the active set of the inequality constraints, and whichever are found active, whichever evaluate to 0, you put them along with the equality constraints. So, bunch active GIs with H temporarily for this iteration, and then you work out the tangent subspace. So, tangent subspace is any vector D which satisfies A D, where A is grad H transpose. This we have studied in the theory, and if H after the composition of active G's has L dimensions, X anyway has n dimensions. So, this matrix will be L by n, and we are taking this as full rank. Okay. If it is not full rank, that is basically the disqualification of the constant qualification condition, and then accordingly you have to drop 1, fine. So, you determine A with these first order derivatives, and then evaluate the gradient and find its projection on M. So, here again have a look at a little picture. So, suppose this is the constraint surface, actually a multidimensional constraint hypersurface, but here we are showing it like this, and this is the current point. Okay. Now, gradient of the function has nothing to do with this. So, gradient of the function could be as well this, okay, and this is the tangent subspace. Now, if this is the gradient of the function or negative gradient, if this is a negative gradient, then its projection is this on the tangent subspace, and it is this tangent subspace projection which you have to take as the gradient vector. Okay. So, evaluate the gradient, find its projection on the tangent subspace, and take that fellow's negative as the search direction. Okay. So, gradient, negative gradient, its projection, and in assignment 1 you must have seen that the projection of a linear transformation is worked out like this. If the matrix is A, then I minus A transpose inverse into A, this gives you this projection. Okay. So, any vector for which you want the projection on A D equal to 0, you have to multiply with that P matrix, which is a projection matrix. Then this perpendicular component is cut off and the tangential component is retained. Okay. That problem appears in assignment 1. It is non-trivial. So, you have a look at it once more. Yeah, this is the one. Let an n minus m dimensional subspace be defined as this, where A is full rank. Okay, this A is full rank. The orthogonal projection of a vector to the subspace is given by the transformation this. Okay. So, that transformation is the one which is being used here. Okay. So, you get the dk as minus projection of the function gradient. Along this direction you will conduct the search, and if this vector itself is extremely small, that is its magnitude is less than epsilon g, that means you have converged. So, you stop. Okay. Otherwise, you do all these things. Okay. If this is not extremely small, if this is non-zero, it is a non-zero vector, then you will conduct a line search along this direction, for which you work out the bounds. Okay. So, that the inactive constraints on the way should not become violated, should not get violated. Active ones will not get violated anyway, because you are moving in the tangent subspace of the active constraints. Okay. So, it is the inactive ones which you should consider to get the line search bound, and then conduct the line search, your standard golden section or whatever it is. Okay. And you conduct the line search and get hold of alpha, and then your candidate for the next iterate is x k plus 1, which is y 0 equal to x k plus alpha k d k. Fine. So, the alpha k that you have got from here you use here, but that is the candidate y 0, because by moving in this direction you might have left the tangent space, you might have left the surface, you are on the tangent space. So, suppose in this direction you are conducting the line search and you have come here. You see, this is not on the constraint surface, maybe outside. Okay. So, from here you have to come down here. You would notice that at this point, in the case of generalized reduced gradient method, we straight away took the Newton-Raphson iteration. Okay. That is one possibility that you could do here also. Another possibility is to work out the perpendicular from here on this surface, but then where is the foot of the perpendicular, you do not know. So, you do not know that corresponding normal. So, you do not know the direction. However, recently you have evaluated a direction already, which is this, okay, and that is grad h, that is already in your hand, that is A, that is a matrix A in your hand. So, why not move in that direction, perpendicular to this itself, like this, okay. Go perpendicular to this and drop here. So, perpendicular to this, how far to go? You see, first you went in the tangent direction to come here, that is for optimality, and now you are going exactly in the orthogonal direction to ensure feasibility back. Okay. So, this direction you know, that is grad h, that is A transpose. Now, you say that I will, from this current y, I will take a step in the normal direction, okay, the normal vector into some distance. Now, this is another alpha. Okay. However, this normal direction may be composed of several directions, because there are several active constraints. Okay. So, this basically means that this alpha is a vector, this line search alpha was a scalar. So, I agree that this using the same notation for these two things was not a good idea, but anyway. So, take it as a vector, okay, and this as a matrix. Okay. So, it is like y 1, y 2, y 3, y 4, y 1, y 2, y 3, y 4, plus grad h 1, grad h 2, grad h 3 multiplied with alpha 1, alpha 2, alpha 3. This alpha 1, alpha 2, alpha 3 is this vector which we want to find out. Okay. So, this alpha 1, alpha 2, alpha 3, that is how much in the grad h 1 direction, how much in the grad h 2 direction and how much in the grad h 3 direction together we should go to reach this surface. This is what we are trying to find out. Okay. So, this is a matrix, this is a vector and this is also a vector. This is a 3 dimensional vector, this is 4 dimensional vector, or you can say this is n dimensional, this is L dimensional. Okay. So, now first order Taylor series gives you h of y plus some matrix into alpha vector is h of y plus grad h at the current point transpose this entire change delta y, that is this. Okay. And this is A, this is A transpose. So, write A transpose and that is the 3 by 3 little matrix, for which just recently you have actually evaluated the inverse. So, you already have the inverse. That is why in this particular case we do not go by the variable direction of Newton-Raphson, we do not go by the unknown direction of the surface normal at the target, we go by the direction of the surface normal at this point. That means, the normal to the tangent space. Okay. So, in order to take this advantage of the direction already in hand, the matrix already in hand, its inverse also is in hand. So, for taking the advantage of all these computational advantages that we already have in hand, we have taken this direction. So, then you want this h at y plus delta y to be 0, that means, this thing you want to be 0. Okay. Based on that you want to work out alpha. So, alpha vector will be A transpose inverse into this, A transpose inverse into this, that is alpha. Put that alpha here, that is y plus A transpose alpha. Okay. So, since this will bring in the minus sign, so that minus sign is here. So, this is the next value for vector y if converged. Now, this is calculation, this does not tell that you have reached that surface. Okay. So, at this y you have to again evaluate h, because anyway it is an iterative process with the help of first order Taylor approximation. So, if converged, if this y satisfies h within your requirement, then fine, you update, otherwise you say that no, it is not converged, this is not enough, we have to do this a little laboriously, and that can happen. As I showed you one situation, if the surface is like this, but it does not go this way, but it goes this way, then moving in this direction will not converge. Okay. Even this moving in this direction will not converge. Okay. So, in that case you can take half and then try, if that also does not work, then you take another half and then try, and so on. Again, half is a convenient factor and you can take your suitable factor here. Okay. So, this is the step if this vector is not extremely small. If this vector is extremely small, that means, if this decay is 0, that means, you seem to be already converged on the local minimum point, seem to be, not necessarily, because remember this is active set formulation, and that means, after having converged to a 0 step iteration, you need to check the Lagrange multipliers, whether the active sets are genuinely active constraints, or some of them is masquerading inside the list of active constraints. So, if this is not so, if you seem to have converged at the solution, then diagnose, okay. Work out the Lagrange multipliers, and why should the Lagrange multiplier expression be this? So, you can work it out very easily. I think we remove this thing, Actually, we should know, because the Lagrange multiplier gives you the rate of change of the objective function in the normal direction. So, that is behind this A transpose inverse A grad f. Okay. But you can mathematically work it out from KKT conditions. You know this grad f plus grad h times lambda equal to 0. This is a vector, this is a matrix, into this is a vector, okay. And grad h is actually A transpose. This list of H has all the genuine equality constraints and active inequality constraints also. Now, you want to solve for lambda, right. So, multiply both sides with A, then you get A grad f plus A transpose lambda equal to 0, and from here you can get lambda as minus A transpose inverse A grad f. This A transpose inverse you already have. Okay. So, that is how you get this lambda as minus A transpose inverse A grad f. This is a list of Lagrange multipliers. Sitting inside that will be the genuine Lagrange the genuine lambdas and actual mu's, that is the Lagrange multipliers corresponding to the equality constraints and active inequality constraints. Scoop out the active inequality constraint Lagrange multipliers and check whether all of those are non-negative. If all of them are non-negative, then indeed this is a KKT point and stop. Otherwise, what do? The worst negative mu that you get out of it, the corresponding inequality constraint you drop from the active set, throw it in the inactive set and continue the iteration all over again. And that means from here. Okay. So, from here the loop starts. Here this if condition is checked. If 0 vector you get for search, then you check the Lagrange multipliers and do this step. If the vector is non-zero big enough, then do all these things, get to the next iterate. Okay. So, these are the two ways to go to the top of the loop, after which you continue. Okay. So, this is gradient projection method, and as I told you, this can be formulated in the slack variable strategy also. Okay. So, next our last method remains, which is feasible direction method, and by now you must have noticed the similarities and differences between the GRG method and gradient projection method. Both have a lot of similarities, that is they try to move in the tangent space, tangent subspace, and then they reach a point which is typically outside, and then from there drop to the constraint boundary and continue. Okay. And why I like gradient projection a little better is that it does not take an a priori sense of dependent and independent variables. Rather, in order to reduce the dimension, it first evaluates the gradient and takes a projection. That is, iteration by iteration it determines what is its direction of movement, rather than there also it is iteration by iteration decided, but the partitioning is decided iteration by iteration. So, it is more rigid in the case of gradient projection. At the point it is decided exactly which direction would be best. Okay. Okay. So, next is feasible direction method, which is a typical slack variable strategy, right. Okay. So, this is our last method in the stock of primal methods. This is feasible direction or Zautendijk's method. When this method was developed, that was long time back, that was the time of the great simplex method in the linear programming problem. And then at that time, anybody working in optimization, if he could break down a nonlinear problem into some way by which it could be solved through linear programming problems, that would be a victory in itself. So, you will see that this Zautendijk's method leans heavily on linear programming. See how it is done. So, typical initial steps and final steps I am not pointing out anymore, that you know. Start the initial point, set k equal to 0 and select as many small numbers as you need as tolerance values and so on. Okay. So, those things you do, and then as you start the iteration from x k equal to 0, 1, 2, 3 whatever, first identify a set of active constraints, and the definition of an active constraint here is actually very stringent. In active constraint you put any constraint for which the constraint function g j evaluates to minus epsilon. Okay. That means, if it comes towards the boundary with a margin of epsilon, small number that you have selected, then itself you start calling it active. Okay. It does not have to go even up to 0. That means, up to 0 you will not even go. So, if it comes to epsilon, you say it is already active, fine. So, you are afraid of touching the boundary. Okay. So, this is how you decide on active constraint, fine. Now, from that point you want to find a direction in which you want to move, and that direction should be a descent direction, a feasible direction, and that means a descent feasible direction. So, for example, there could be several boundaries close by, that means several constraints which are active like this, and there is this objective function f. So, if you are operating somewhere here, then that means you are within epsilon margin from this constraint as well as this constraint, and from here you want to make a movement which will reduce the value of this g and reduce the value of this g also, hopefully. Okay. So, that means you want to move in this direction, you want to move in this direction. That means, basically you would move somewhere along this, that is either this or this or this and so on. So, in some of these directions, and over and above that you want the function also to decrease. That is the idea of optimization, fine. Now, in 2D board I am drawing, so you are not getting enough dimensions. Think of another surface, the function contour like this, and from there in the 3D then you can think that you have to come inside the cone. Inside the cone defined by the contours of all the active g's and the contour of active contour of the objective function f, that is whichever is the local contour of objective function f and the 0 contours of the active constraints. Okay. So, with respect to all of them you want to come inward. Okay. So, you want to come such that you want to take a direction, a descent feasible direction, in which direction the component of grad f is negative, component of grad g j, one of the active constraints, is also negative, another g j also negative, and so on. And then say that if one of them is minus 3, another is minus 2, another is minus 1.5, then you say that can I not sacrifice the minus 1.5 a little, so that I can bring that minus 3 a little closer. Okay. So, I mean, or rather the other way around, that minus 3 is a great thing, minus 1.5 is very close to 0. So, you want to sacrifice one of them where you have play to improve the other. So, you say that I am looking for the best d, where all of these, say one of the objective function fellow and several of these active constraints, all of these will have the same margin. Okay. So, such a direction, get me such a direction. Okay. So, how to find a descent feasible direction such that all of these have the same margin from 0, same margin and best margin. Okay. So, this is what you want. So, the best such direction you want. So, and then you say we are right now looking for direction only, but then as direction 132 and 264 is the same thing. So, we want it to be bounded, we do not want the numbers to go into thousands or whatever. So, for that one thing you could do, you could also say that I want the direction such that it is a unit vector, but that you do not say, because unit vector will mean d 1 square plus d 2 square plus d 3 square, and this is a nonlinear relationship. You do not want that, because you are going to use linear programming, make note. So, you say that we do not do that, we do not take the directions in a sphere, I mean direction vector bounds as on the sphere, but we take it on a cube. Okay. So, something equivalent will be achieved. So, you say that mod of d I is less than or equal to 1. So, that is how we will work out the d 1, d 2, d 3, d 4, the direction vector. Now, this is linear enough, which is fine, because this splits into two inequalities. One is d I is greater than minus 1 and the other is d I is less than 1, which is fine. But then you are going to set it in the form of a linear programming. So, you say that this minus 1 to plus 1 is not working fine. It would be nice if we shift it and make it 0 to 2. So, then in place of d i's you put s i's. Okay. So, s I is equal to d I plus 1. So, now for changing d I from minus 1 to 1, that is varying d I between minus 1 and 1, you will basically vary s I from 0 to 2, and that fits very well for the linear programming framework. Then you say get me the maximum margin beta subject to this being less than minus beta, this being less than minus beta, and so on. Okay. So, these things when you try to work out from d in terms of s, then you see how it will work out. See grad f transpose d, this is grad f transpose. D is now s minus 1 1 1 1 1 1 vector, right. So, d I is s I minus 1. So, put it there s I minus 1, okay. Should be equal to less than equal to minus beta, fine. So, get beta here and get the second part there. So, when you open this, actually this is supposed to be a vector, s 1 minus 1, s 2 minus 1, s 3 minus 1, and so on, s n minus 1. So, when you open this, you will get this grad f transpose s vector minus grad f, that is del f by del x 1 plus del f by del x 2 and up to this, that is sum of all these partial derivatives. From that side import beta on this side, and then this sum of the partial derivatives keep on this side. Okay. So, this is the constraint that you get with unknowns, that is variables s, and this is s vector, okay. Vector s and scalar beta on this side and known things here. So, this the way you do for f, similarly you do for g 1, g 2, g 3, whatever active constraints are there. Okay. So, this one and this several for all the j's in the active set. Other constraints, that is bounds, s I, each of them should be less than or equal to 2 and each of them should be greater than or equal to 0 and beta also should be greater than or equal to 0. So, you have got the linear programming problem set up. Now, solve it. linear programming problem everybody knows how to solve. So, they solve it in terms of these variables, so many s variables and one extra beta, and the objective function is just beta. Okay. So, you maximize beta for all these things. You solve it and get the s. After you have got the s, solution s, from there work out the d, okay, that is s minus 1. So, each s component, from that you subtract 1. So, whatever s you get from this solution between 0 and 2, after you subtract 1, you get them minus 1 to 1, and that gives you a direction vector. If this direction vector turns out to be 0, then you stop, and that means you have converged. No more need to check anything, because all the necessary precautions you have taken here itself. Okay. If this is not 0, if this is not extremely small, then you conduct a line search in this direction. So, perhaps you have decided on an interior direction in which the function is going to decrease and all the active constraints are becoming a little more relaxed. Okay. So, that is what is happening by this optimization, by this linear optimization. So, work out the bound on the line search, maximum alpha u you work out from the bounds, variable bounds, okay, that is from the current point in this chosen direction, how much can we go, so that we do not violate any of these limits. So, that alpha u decide, and if necessary you may need to curtail, because if that alpha u, after satisfying all these variable bounds, if it still makes some of these fellows as greater than minus epsilon, then you still curtail, okay. Thereby determine alpha u to ensure that this line search will never take you outside the domain or even near the boundary of the domain. You see, this is not 0, this is minus epsilon. Then conduct the line search. Okay. After you conduct the line search, get alpha and then update. Nothing else to check, because everything, all the precautions you have taken here and at the top here. Okay. So, this is feasible direction method, which is really scared of infeasible regions. Okay. So, this method can be useful for those problems in which objective function cannot even be evaluated outside the domain, outside the feasible domain. So, there this method will work fine, because in this method you are never evaluating anything outside the domain. Now, questions that remain: what to do with equality constraints? This is going to be trouble, because Zautendijk's method actually has no arrangement to take care of equality constraints. One possible way to handle that is this, that is h I is less than epsilon and minus h I is also less than epsilon. This is one way to handle it. That will basically allow you a little channel around the h I surface. The other option is, one side you handle with this epsilon margin and the other side you handle with a penalty function. Okay. So, these are two ways of handling equality constraints. Whichever way you handle, handling of equality constraints is not very convenient in the case of feasible direction method. Okay. So, here our primal methods are over, and all of them are really cumbersome and too many small steps have to be done, but they are reasonably good methods. And in the next lecture, we will take up dual methods. Okay.